Hello, welcome back to Shakil's physics classes. Previous class, we have stopped deriving expression for Lagrange's equation starting from D'Alembert's principle. If you remember the equation, we have derived d by dt of dou L by dou Q dot J minus dou L by dou Qj is equal to 0. This is the expression we derived last class. Today, we are going to see the applications of this Lagrange equation. The first example we are going to see is the simple pendulum, which we have studied from our lower classes. So, we will start with simple pendulum. Simple pendulum. Let me draw a simple diagram for this. This is a bob, metal bob, suspended to an inextensible string. I give a small push. This starts oscillating at any instant of time. Let us say the bob is somewhere here. Okay? Now, and okay. I will call this as H. And at this point, let us say potential energy is 0. This is O. This is the mean position A. At any instant, the bob is at B. The angle subtended is theta. Let this be L. This be C. What is this? A bob, metal sphere, when suspended with a thread. It is a simple pendulum. You give a small push. It oscillates, executes simple harmonic motion. Now before we start, I would like to tell you a few assumptions we make here in applying Lagrange's equation. We consider this metal bob of mass m. This is attached to a inextensible massless string. The length of the string, as I have denoted it as L. The next assumption we make here is air resistance. Air resistance is effect of, I will put it this way, effect of air resistance. Effect of air resistance is negligible on the motion of the pendulum. These are the assumptions we are making here. We are considering a metal bob. Mass of the metal bob is m. It is suspended using an inextensible massless string of length L. Effect of air resistance is negligible on the motion of this pendulum. If I displace this pendulum, this bob A, from its mean position, it will execute simple harmonic motion. It executes simple harmonic motion. And mind you, this B is not the extreme position, it is the position at any instant of time, and as I said, L is length of the pendulum. So common knowledge, when it keeps oscillating, it will certainly have kinetic energy. Okay, therefore I write the kinetic energy of the ball. I am denoting kinetic energy as T because in my previous derivation for Lagrange's equation I have denoted kinetic energy as T, and therefore I write it as half mv square. Now where is the v? Let us say this displacement, which is the amplitude, I will take it as x. Okay. If I take it as x, from this diagram, x is equal to L into theta. I suppose you understand that. X is L times theta. Now we have to replace v in terms of x, this angular displacement. Therefore, if I differentiate once with respect to time, which I can denote it as x dot, L being a constant, this becomes theta dot. Is that okay to you, sir? Therefore, my expression for total, kinetic energy will become T is equal to half m. In the place of V, this is equivalent to V as well, okay? This is equivalent to V. Therefore, I write L squared theta dot squared. Theta dot squared. This is equation 1, which gives me the expression for kinetic energy. It is oscillating and therefore definitely will have kinetic energy. In the mean position, potential energy is 0. At that instant, what is its potential energy? We know the potential energy of the ball. This I will denote it as V. I know this is mgh. Am I right, sir? This is mg. This h I want. This h, can I write it as OA minus OC? Therefore, OA minus OC will be h. Now we'll try to see what is OA. OA is the length of the pendulum L. Therefore, mg into L minus, we want this OC. If you consider this as a right angle triangle, OC will be L cos theta. This will be L cos theta. Therefore, I write L cos theta. If you don't know this, how this is L cos theta, you are not fit to sit in second BSc. This is hypotenuse, this is opposite side, this is adjacent side. Cos theta is adjacent by hypotenuse. Therefore, adjacent upon L is cos theta. Therefore, adjacent side is L cos theta. That is what I want. Is that okay to you? I will call this as equation number 2. Okay, sir? That is equation 2 for me. Now, let us write the Lagrange's equation. From Lagrange's equation, this can be written as dy dt of dou L by dou Q dot J minus dou L by dou Qj is equal to 0. And we know from transformation equations, Lagrangian L is a function of Q, is a function of Q dot, is a function of T as well. So, for this system, Lagrangian L is T minus B. Therefore, you write L is equal to T half m L square theta dot square minus m G into L minus L cos theta. We have written the Lagrangian here, right? Now, the Lagrangian general equation has to be modified to fit in for our system. How do I write that? For our system, the Lagrangian equation, d by dt of the variable is theta, therefore dou L by dou theta dot minus dou L by dou theta is equal to 0. That is the Lagrangian equation for us. Okay, let me call this as equation number 3. Now from the L which we have to find out dou L by dou theta and dou L by dou theta dot. So dou L by dou theta dot half m L square 2 into theta dot. 2 will go off to give me m L square theta dot. Is that clear? Now, dou L by dou theta, MGL will go off, minus or minus plus. Therefore, MGL cos theta, if you differentiate, minus sin theta, minus sin theta. So we have got expressions for dou L by dou theta dot and dou L by dou theta. We need to substitute these values in equation 3. Which one shall I rub off? Please tell me. Shall I rub the diagram where I have said a simple pendulum is nothing but a bob connected to an inextensible master string of length L, and OA is its equilibrium position. When you give a small push, it oscillates and it executes simple harmonic motion. B is the position of the bob at any instant of time. The important assumption I have made is effect of air resistance in the motion of the pendulum is almost negligible. Okay, I will rub this off. Therefore, substituting in equation 3, d by dt of m L square theta dot minus of minus will become plus, am I right? Plus mgl sin theta is equal to 0. ml squared is a constant, L squared constant. If you differentiate with respect to time, theta double dot plus mg L sin theta is equal to 0. Dividing this expression throughout by ml square, I get theta double dot plus g by L, am I right? G by L sin theta is equal to 0. Theta double dot plus G by L into sin theta is equal to 0. I make an assumption here if approximation, if the amplitude of motion is small, then sin theta can be approximated to theta itself. Therefore, this equation becomes theta double dot plus G by L into theta is equal to 0, which is the equation of motion of a simple pendulum. If you are not able to recognize this, we go to the lower class where we have studied. I will rub this off. Okay? Where we have studied d square theta by dt square is equal to minus G by L into theta for a simple harmonic motion of a pendulum. Is that okay to you? This d squared by dt squared is angular acceleration, a constant minus omega squared theta, where omega squared is G by L, omega is G upon L. Therefore, the time period T is 2 pi by omega. Therefore, T is 2 pi under root of L by G. That will be the time period. So, what will be the frequency? F 1 by 2 pi root of G by L. That will be the expression for frequency. This is how we apply Lagrange's equation to arrive at equation of motion of a simple pendulum. Is that okay to you, sir? If this is okay to you, we go into the next application, compound pendulum. Let me rub this off. Lagrangian of compound pendulum. Let us first try to draw a simple diagram. Okay. Theta L C P A. Okay, that is X and G. Okay, let us first try to understand what is a compound pendulum. Is a rigid body capable of oscillating in a vertical plane in which this compound pendulum is oscillating about a fixed horizontal axis. The horizontal axis is like this, passing through the point O. I am not writing this on the board, so please listen to me. I will try to repeat it once again. A compound pendulum is a rigid body capable of oscillating in a vertical plane about a horizontal axis, passing through the point O. The vertical plane in the diagram, I have denoted it as XY. As I already told you, O is the point